Hi guys, I welcome you to my YouTube channel, Learning Physics with IBM. And remember, we have started episodes of kinematics and dynamics. Don't forget, these are solved past paper questions in kinematics and dynamics. This is AS Physics 9702, and we are dealing with the multiple choice questions. I think we are done part 1, and this is going to be part 2. So without wasting time, I would like to take you to the document so that we start solving the questions for part 2. So in part 1, I think we stopped here. Remember, this unit is heavy, it's quite heavy, it's just like waves. It also carries more marks. Kinematics and dynamics combined could also contribute about 8 to 10 multiple choice questions. So the questions are quite heavy in understanding, and therefore the videos could be 1 hour, but the questions solved could be very few in that time. Okay, let's get started in part 2. So an object falls freely from rest in a vacuum, so that means there is no air resistance. The graph shows the variation with the time t of the velocity v of the object. So if there is no air resistance, of course we see that this one is showing that the gradient is constant. So the acceleration is constant. So here acceleration is constant for that particular graph. It is constant and not zero. So that is in a vacuum. Which graph using the same scales represent object falling in air? So if there is air resistance, the acceleration is not constant, which makes A to be wrong. If there is air resistance, the acceleration is bound to decrease and will tend to zero. So the acceleration should tend to zero. And how do we show that? It means the gradient should decrease to zero if the acceleration decreases. So D is automatically wrong because it shows that the acceleration increases, because the gradient in D is increasing. Here gradient is increasing. Here the gradient is increasing, which means the acceleration is increasing. So we have to choose between B and C. Now, if there is air resistance, the acceleration decreases to zero. It means we reach terminal velocity, and we can't reach the same maximum velocity as before. This is what makes B to be wrong, because B is showing that if this is the maximum velocity we have represented in the diagram, it also shows that in the same time it reaches maximum velocity, the same maximum velocity before it becomes constant. But this is not true. As acceleration decreases, it means using the same scales, we don't reach the same maximum velocity as before. So the terminal velocity will be less, the maximum velocity will be less than the maximum velocity in the previous case when there was no air resistance. This is what makes this one to be correct. The gradient is decreasing, which means acceleration decreases. That means it reaches zero. It tends to zero before reaching the maximum velocity that we have in the previous part. So it reaches zero before reaching the previous maximum. When I talk about the previous maximum, I'm referring to the graph where there was no air resistance. So that means the maximum velocity is going to be below the maximum when there was no air resistance. So the answer is C. The curved line PQR is the velocity time graph for a car starting from rest. It is starting from rest. What is the average acceleration of the car over the first 5 seconds? Over the first 5 seconds, average acceleration. Remember, average acceleration is actually the gradient. So the area below the curve PQ, area is not the acceleration. The area of the triangle, remember, area is not the acceleration. The gradient of the straight line PQ, the gradient of the tangent at Q. Now we want the average acceleration over the first 5 seconds, not the acceleration at 5 seconds. So it means the answer is going to be C rather than D. If we wanted the acceleration at 5 seconds, at t equals 5 seconds, then we would draw a tangent, we would take a tangent. But since we want the average acceleration over the first 5 seconds, then we take the gradient between P and Q, which is going to be C. So the last one, this one is acceleration at P, or at Q, exactly at Q. That would be acceleration at Q. A ball is thrown horizontally with a speed of 10 meters per second above horizontal ground. The ball hits the ground after a time of 3 seconds. Air resistance is negligible. That means the equations of motion can apply. So maybe I can sketch horizontal projection. The ball is projected horizontally, so it follows follows that path. Initial velocity is 10 meters per second. What is the speed of the ball just before it hits the ground? Just before it hits the ground. Okay. So first of all, we may choose to find the horizontal displacement, or we may choose to find the vertical displacement first using S equals to UT plus a half AT squared. If air resistance is negligible, then the motion is uniformly accelerated. So the Suvart equations, you can now use Suvart equations. The Suvart equations can now apply. So using S is equal to UT plus a half AT squared. You remember this part, initial velocity is 0 in the vertical. If I consider vertical motion, initial velocity is 0. Acceleration in the vertical is 9.81. So this is going to be a half times 9.81, then times t, which is 3, but squared. So when I check with my calculator, I have 0.5 times 9.81 times 3 squared. This is going to be approximately 44 meters. That is a vertical displacement. Then I can use v squared equals to u squared plus 2as. I'm finding v in the vertical, so I'm considering vertical motion. Remember, initial velocity in the vertical is 0 because it was initially moving horizontally. So v squared here is going to be equal to 2 times acceleration is 9.81, then times s, which is 44, which means when I find the square root, or even if I don't find the square root because I'm again going to square it, then this is going to be 2 times 9.81 times 44. So v squared is equal to 863. Of course, this is going to be meters squared per second squared because I did not find the square root. Okay, then when the body hits this point, the velocity has two parts. The resultant is what we are looking for, but there's velocity in the horizontal which remains 10. Then there's velocity in the vertical, which we have just found v in the y, which we have just found as the square root as the square as 863. So we find the resultant. The resultant velocity is going to be the square root of 10 squared plus v in the x squared plus v in the y squared. Remember, v in the y squared is 863. So this means v resultant is going to be the square root of vx squared is 100 plus vy squared is 863. So I'll just press my calculator. Square root of 100 plus 863, which gives me 31. So v resultant is 31. So the answer is going to be C. An object is moving along the ground in a straight line at a constant speed where acceleration is going to be 0. Which statement about the resultant force acting on the object is correct? So if the acceleration is 0, force is equal to mass times acceleration, then it means the resultant force is going to be 0. So the resultant force acting on the object is equal to its weight. The resultant force acting on the object is equal to the product of its mass and its velocity. The resultant force acting on the object is equal to the resistive force. The resultant force acting on the object is equal to 0. So the answer is going to be D. When the acceleration is 0, then the resultant force is 0. So the answer is D. Water flows out of a pipe and hits a wall. When the jet of water hits the wall, it has horizontal velocity v and cross-sectional area A. Horizontal velocity, this is horizontal velocity v and cross-sectional area A. The density of water is rho. The water does not rebound from the wall. What is the force exerted on the wall by the water? So first of all, we know that density is mass over volume, so the mass is going to be density times volume. And of course, we know that volume is cross-section area times another length. Or, okay, cross-section area times another length. So let that length be the distance which the water moves. So the volume is going to be the cross-section area. That length is going to be L is going to be V, speed times time. So this is going to be V, small v times T. This is capital V for volume, and this is small v for speed. We also know that force is the rate of change of momentum, which is going to be mass into change in velocity. It is, let's say, it has horizontal velocity v. When the jet of water hits the wall, it has velocity v and cross-section area A. The water does not rebound, so final velocity is 0. So we shall say v for velocity minus 0. Remember, capital V is volume and small v is for velocity, which is horizontal velocity, minus initial velocity, final velocity, which will be 0 because it does not rebound. Then we divide this by T. So it means force is equal to mv divided by T. But remember, the mass is density times volume. So this is going to be density, which is rho, volume, which is cross-section area, times speed v, then times T. No, this is not volume, it is velocity. Okay, so this is only this is mass. Then I'll say times v, this v here. So times this v here, then divide by time t. So the time t cancels out, and the v is going to be squared. So the force is going to be density cross-sectional area times v squared. So I think this makes the answer to be D. So our answer there is D. A projectile is launched at an angle above horizontal ground and travels through the air. The projectile reaches its maximum height at position X. Assume that no upthrust acts on the projectile. Which diagram shows the directions of the forces of the force or forces acting on the projectile at point X. So of course, this is it has a mass, so it has a weight which should be vertically downwards. So this is the weight. It has a weight which is vertically downwards. It is traveling through air. If it is traveling through air and it has been projected onto this side, it has been projected on this side here because it is moving to the right. So it has been projected onto this side. It means the air resistance must be in the opposite direction. So the projectile reaches its maximum height at position X. So when it is just at x, the only velocity acting is velocity in the horizontal. Velocity in the horizontal is there, but velocity in the vertical is 0. So v in the y is 0 here. It's only velocity in the vertical which is acting to the left to the right hand side. So the air resistance must be acting to the left hand side because it is moving. This is velocity and the x is to the left, to the right. The air resistance must be to the left. So the weight is acting vertical downwards. So the air resistance is acting to the right, to the left, because it is moving to the left in the horizontal, because the velocity in the horizontal is to the right. So it means our answer is going to be automatically B. The weight vertically downwards. So of course C and D are wrong because they don't take into consideration of air resistance. What makes A wrong is because at point X, velocity in the Y goes to 0. Velocity in the X is to the right hand side. Therefore, air resistance must be to the left-hand side. If velocity is to the right-hand side, air resistance must be to the left-hand side. So the answer is going to be B. What is the statement of the principle of conservation of momentum? So we know that for an isolated system of interacting bodies, the total momentum is always constant. Or the total momentum, I don't always want to use the word conserved, but remains constant. So the answer here is automatically D, without wasting time. Total momentum of a system of interacting objects remains constant provided no resultant force acts on the system. So when no resultant force acts on the system is said to be isolated. So the answer is B. A car travels anti-clockwise along the horizontal circular road of radius 12 meters as shown. The car takes a time of 4.0 seconds to move from position P to position Q, P to Q. So it is moving anti-clockwise. What is the magnitude of the average velocity of the car for the journey from P to Q? Okay, so since velocity is a vector quantity, then first of all, I will just consider the displacement from P to Q. I will need this displacement here. The displacement, the shortest distance between P and Q, which is that one there. So this is 12, this is also 12. Let's find that displacement, PQ. So the displacement which is P to Q or QP, I will call it QP, the shortest distance between Q and P. Of course, we are using Pythagoras theorem. This is going to be the square root of 12 squared plus 12 squared, which is going to be equal to 12 squared plus 12 squared, root of the answer. So the root of the answer is 16.97. So that is the displacement. Then to find the speed, the velocity, we shall get the displacement divided by time. So displacement is 16.97 divided by the time, which is 4 seconds. So we shall divide that by 4, which gives us 4.2. So this is 4.2. So the answer is going to be A. Remember, since it is velocity, average velocity, we need to take the displacement. And the displacement is the shortest distance between the starting point and the point where you are. So it is the distance between the P and the Q, not the other path which has been taken, not the circumference, and so on and so forth. Shortest distance. So the answer is 4.2 meters per second. The water surface in a deep well is 78.0 meters. Below the top of the well, a person at the top of the well drops a heavy stone down the well. Air resistance is negligible. The speed of sound in air is 330 meters per second. What is the time interval between the person dropping the stone and hearing it hitting the water? So dropping the stone and hearing it hitting the water. Okay, so if we assume air resistance is negligible, so equations of motion can apply. So I'll first of all find the time it takes to hit the water using the equations of motion or the Suvat equations. So S is equal to ut plus a half at t squared. So it is going to fall, when it hits the water, it falls a distance of 78 meters. This is equal to, assuming it starts from rest, because the person at the top of the well drops. So assuming it starts from rest, initial velocity is 0. So this will be equal to a half times 9.81. Since air resistance is negligible, the acceleration will be the acceleration due to gravity. So then times t squared. So I'm trying to find the time it takes to hit the water. So we have so we're going to have 78 times 2 divided by 9.81 square root of the answer. So I'm getting 3.99. So the time is 3.99 seconds to hit the water. So it means to hear the sound, the time, of course, the sound must return back. So for sound, let's find the time it takes to reach the person. So to hear the sound, this is to hit. So to hear the sound, so the time taken for the sound to reach the person must be, of course, is going to travel the same distance over the speed. So the distance is going to be still 78. We are now looking at the sound leaving the bottom. So 78 plus the speed of sound, which is 330. So this is going to be 78 divided by 330, which is 0.24. So this is 0.24 seconds. So this is the time, the speed, the sound takes to leave the bottom to the person. So what is the total time interval? So the total time interval is going to be the sum of the two values, 0.24 from the bottom to the person plus 3.99 from the top to the bottom. So that the total is going to be 4.23. So this is 4.23 seconds, which means our answer is going to be D. Because of rounding off this, the answer is approximately D. If I had taken most decimal places, for example here, I would have taken 4.98, 3.998, I mean 3.8988. And I would have taken here 0. I think it was 236. If I add that, 3.988 plus 0.236, that will give me 4.224. So it means the answer is going to be D. Which statement is not a requirement? Not a requirement of a pair of forces that obey Newton's third law of motion. A pair of forces that obeys Newton's third law of motion. Of course, remember Newton's third law of motion. When body A exerts a force on body B exerts an equal but opposite force on body A. That is, FA, this should be equal to minus FB. When body A exerts a force on body B exerts an equal but opposite force on body A. So which statement is not a requirement of a pair of forces that obey Newton's third law? So remember, these two forces act in opposite directions. That is very true. The two forces act on two different bodies. That is very true. A exerts a force on B and B exerts a force on A. So that is very true. The forces act on objects in contact. They may not, this is not a requirement. It's not a requirement that the forces act on objects in contact. The objects may not also be in contact. It could be two like charges, charge A and charge B. If they are charged spheres, this is positive and this is positive, and they are repelling each other by Newton's third. They may repel each other with a force which is equal but opposite, so they do not need to be in contact. When you go to A level, you'll talk about gravitation, where two masses attract each other with a force which is directly proportional to the product of the masses and inversely proportional to the square of their separation. These two masses do not need to be in contact, but the force of attraction of one mass by another is equal but opposite to the force of attraction of another mass by the other. So normally these forces are equal in magnitude, so this is not a requirement. It's not a requirement. So the answer is C. A child of mass 20 kilograms, stands on the rough surface of a sledge of mass 40 kilograms. The sledge can slide on a horizontal frictionless surface. One end of a rope is attached to the sledge. The rope passes around a fixed frictionless pole, and the other end of the rope is held by the child, as shown. The rope is horizontal. The child pulls on the rope with a horizontal force of 12 newtons. This causes the child and the sledge to move with equal acceleration towards the pole. What is the frictional force between the child and the sledge? What is the frictional force between the child and the sledge? Okay, so there is a forward force from the child from this rope which is pointing this side, and this is a force of 12 newtons, and that means the sledge is also exerted because the sledge is also being pulled. So there is also a forward force of 12 newtons in this rope on the sledge. This is 12 newtons. So I want to draw a different diagram for simplification. But then anyway, there's friction. There's friction on the there's going to be friction force. Let me just draw a different diagram. So I'm going to draw the sledge like this. I'll draw the sledge like this. And I'll put the child with a different color. I'll put the child as just an object like this. So let's put the forces. First of all, there is a forward force on the child of 12 newtons from the rope, and there is a force of 12 newtons on the sledge itself. That's number one. So for equilibrium, first of all, there is friction. There must be friction force on the child because the child is tending to move forward. There is friction force between the child and the sledge, which I'm going to call FC. And also, there should be a friction as the sledge moves forward. There should also be a frictional force on the sledge which is forward, because as the child tends to move forward, the frictional force on the child is backwards, but then there should be a frictional force on the sledge which is going to be forward, and that is going to be Fs. So these two forces are going to be equal, and I will just represent them by Newton's third law. These two forces are going to be equal, and I'm just going to represent them by F. So frictional force on the child is the same as the friction experienced by the sledge, which is simply going to be F. This is going to be by Newton's third law. Okay. So using equilibrium principles, let's look at these forces. The resultant force by Newton's third law is given by Ma, which is going to be equal to 12 newtons minus F. That is by Newton's third law. So for the child of mass 20, so this will be 20 times its acceleration A is equal to 12 minus F. Then if I consider the sledge itself, and I use the same expression, then the mass is 40, the acceleration is the same A, then the force on the sledge, this will be 12 newtons, but remember the friction Fs is actually the same direction as the 20 newtons for the sledge. So this is going to be plus F. So when I add these two equations, or whatever I do when you add the two equations, or if you divide, okay, let's try to add the two equations. When I add the two equations, I have that 40 So how do I want to solve this? Okay, let's first, I didn't want to find acceleration, I just wanted to find F directly. So okay, to find F directly, I'll just divide. So I will say 40 A divided by 20, A should be equal to 12 plus F divided by 12 minus F. So A cancels out. And if A cancels out, I remain with the 2 into 12 minus F, because 4 over 2 is 2, should be equal to 12 plus F. So solving this equation, I'm going to have 24 minus 2F is equal to 12 plus F. So collecting like terms, I have 12 on one side equaling to 3F, which means F is simply going to be 4 newtons. So it means the answer is automatically going to be A. So as the child tries to pull, this tends to pull forward, there's friction on the child in the opposite directions. As the sledge tends to move, as the friction tends to as the friction from the child tends to move forward, then the friction on the sledge is going to actually forward. If the friction on the child is backward, then the friction on the sledge is forward. And by Newton's third law, these two forces are equal, and I just called it F, as simple as that. So the answer is automatically going to be C. Of course, this is quite technical. It is quite advanced, but then that is fine. The answer is going to be A. A stone S and a foam rubber ball are identical spheres of equal volume. They are released from rest at time t equals to 0 and fall vertically through the air. Both reach terminal velocity. That means they reach a constant velocity. Which graph best shows the variation with time t of the speed v of the stone and the rubber? They have equal volume, but a stone and a foam rubber cannot have the same weight. So the weight of the rubber is most likely going to be less than the weight of the stone. The weight of the rubber is going to be less than the weight of the stone. And remember, terminal velocity is going to depend on this weight. So the terminal velocity for the rubber is going to be less than the terminal velocity for the weight, because if rubber has a smaller weight, even if they have equal volume, if it has a smaller weight, it will travel a very short distance before reaching terminal velocity. That means it will gain a smaller terminal velocity. So the terminal velocity, I'll call it Vt for rubber, is going to be less than Vt for the stone. So the terminal velocity for rubber should be below. So this means this is wrong. This one is showing that they have the same terminal velocity. This one is also showing that finally the terminal velocity become equal. So that is not true. So it means the answer is going to be B. The terminal velocity for rubber is going to be less than the terminal velocity for the stone, because if the volume is the same, then terminal velocity will be determined by the weight. A lighter object has a smaller terminal velocity than a heavier object if they have the same volume. So they experience the same air resistance. I mean, they do not experience the same air resistance, since for a falling object, the weight is constant, but the air resistance increases, and air resistance affects more the lighter object than the heavier object. So that means the one which is lighter reaches terminal velocity in a short time, and therefore it gains a smaller terminal velocity. So the answer is B. Two balls X and Y are moving towards each other with a speed 5 meters per second and 15 meters per second respectively. They make a perfectly elastic head-on collision. That is very simple. It means relative speed of approach should be equal to the relative speed of separation. Let's say to the right hand side is positive, to the left hand side is negative. They make a perfectly elastic head-on collision, and the ball Y moves to the right with a speed of 7 meters per second. What is the speed and direction of the ball X after collision? Okay, let's first begin with the speed. Remember, for perfectly elastic collision, relative speed of approach should be equal to relative speed of separation. So relative speed of approach is 5 minus negative 15, because positive to the right, negative to the left. This should be equal to the relative speed of separation, which is going to be 7 minus x. We don't know what x is. Minus the speed of x. They have said y moves to the right, and we've said velocities to the right are positive. We don't know whether x moves to the left, but we shall see if x is positive, then it moves to the right. If x is negative, then it moves to the left. So this means 20 equals to 7 minus x. And by simple calculation, you notice that x is going to be negative 13. So the negative means it moves to the left. So this minus here means it moves to the left. So the answer is automatically going to be B. 13 meters per second to the left. Two projectiles X and Y are fired into the air from the same place on level ground and reach the same maximum height. Projectile X is fired vertically, X is vertical, and Y is fired at an angle to the horizontal. Air resistance is negligible, so both of them acceleration is 9.81. If air resistance is negligible, which statement is correct? If they reach the same maximum height, it means they are going to take the same time to move upwards and coming back to the same ground, the same level. So X and Y are at rest at their maximum heights. Which statement is not correct? Y is not going to be at rest at its maximum height because it moves in the horizontal, not in the vertical. So this one is going to be out. Because Y is projected at an angle in the horizontal, it is not at rest. There is velocity in the horizontal. The velocity in the horizontal remains constant. It's only velocity in the vertical which goes to 0. X at maximum height will momentarily stop because it's only moving in the vertical. X and Y are fired with the same speed. X and Y are fired with the same speed. Two projectiles X and Y are fired into the air from the same place on level ground and reach the same maximum height. Same maximum height. They may not be fired at the same speed to reach the same maximum height. X and Y take the same time to return to the ground. That one will be very true, because if I consider vertical displacement, v squared equals to u squared plus 2a s. At maximum height, both of them have initial velocity in the vertical, if I consider vertical motion. So this one will be, this at maximum height, this one will be 0 for both when we consider vertical motion. Initial velocity in the vertical may not be the same, but acceleration is the same and s in the vertical is the same. So it means we can find our initial velocity in the vertical, but then if I consider s is equal to ut plus a half at squared, the displacement for both is going to be 0 and the acceleration is the same. The displacement in the vertical is going to be 0, the acceleration is the same. Since there is no air resistance and acceleration is the same, then it means the answer is going to automatically be C, because both objects are going to be accelerated vertically upwards at the same rate, and they will return downwards at the same rate. So that is, for every 1 second, their speed changes by 9.81 meters per second, either going upwards or coming downwards. So it means the answer is going to be C. Of course, they do not, in the vertical, they travel the same distance, but in the horizontal, they do not travel the same distance. A small glider moves along a horizontal air track as shown. At each end of the air track, the glider has a perfectly elastic collision with a fixed buffer. The glider moves, it is perfectly elastic. The glider moves at a constant speed between the collisions. Constant speed between the collisions. So this means this should be a horizontal line for velocity time graph. Which graph represents the variation with the time t of the velocity v of the glider as it moves between the two buffers? A small glider moves along a horizontal air track as shown. At each end of the air track, the glider has a perfectly elastic collision. That means the speed, the velocity does not change. The maximum velocity does not change. So this one is showing a change, that the velocity decreases. This one has also shown a decrease in the velocity. So it means it is not a perfectly elastic collision. Let's check the next ones. Of course, we have to choose between C and D because we see that the velocities are remaining the same. So the velocities in C and D are remaining the same, but then the answer is going to be D, because the distance between the buffers is remaining constant. So it means this part here is not reflecting that the distance between the buffers has remained constant. So the velocity is constant, but the distance between the buffers is remaining constant. The glider moves at a constant speed between collisions. At each end of the air track, the glider, what is this? Sorry for that. So because the distance between the glider is constant, if the velocity is constant, then the time should also be constant. So it means the graph will be this one here. So this one is showing that the velocity is remaining constant, but then it takes a shorter time between the gliders, which means the distance between the buffers has changed, yet it hasn't. So the answer is D. A car accelerates from rest. The graph shows the variation of momentum of the car with time. It's a graph of momentum. What is the meaning of the gradient of the graph at a particular time? So we know that force is defined as the rate of change of momentum. So if I have a graph of momentum, so change in momentum is equal to force times time. So if I try to find a gradient of momentum time graph, I think that is force, or the resultant force actually. So the answer here is automatically D. The resultant force is the rate of change of momentum. A ball is dropped onto horizontal ground and bounces vertically upwards. Vertically. When the ball is in contact with the ground, the following forces act: the weight of the ball, the contact force P exerted on the ground by the ball, the contact force N exerted on the ball by the ground. When the ball is in contact with the ground, the ball is momentarily stationary. For a small period of time, it is momentarily stationary. At this instant, which relationship is correct? Now, I want you to note that at the point of contact, the normal reaction from the ground to the ball should be equal to the normal reaction, the reaction or the force downwards, which is uh, from the ball to the ground. The contact force exerted on the ground by the ball should be equal to the contact force exerted by the ball on the ground. That is in accordance to Newton's third law. Since it bounces, because it bounced vertically upwards, then it means the force which is from the ground to the ball should be greater than the weight. Since it bounces, then the force which is from the ground to the ball should be greater than the weight. In other words, the resultant force must be upwards, and the only force acting upwards is N. So it means N is going to be greater than the weight since it bounces. It goes upwards after the collision. So it means momentarily the resultant force is going to be upwards when it starts moving upwards. So it means the answer is going to be D because it rebounds. So the answer is automatically D. A person stands on the sledge on the edge of a high cliff that is next to the sea. The person throws the stone vertically upwards. Air resistance acts on the stone. This is the changing factor. Air resistance is acting. The stone eventually hits the sea. Of course, if air resistance acts, we must reach terminal velocity. We must always remember that. If air resistance acts, terminal velocity must be reached. Which velocity time graph best shows the motion of the stone from when it is released until it hits the sea? Of course, it should be a graph which has where the gradient becomes constant. So we ignore this one. Where the gradient tends to 0. This one is a constant gradient throughout. It is not factoring in air resistance. The person stands on the sledge of a high cliff that is next to the sea. The person throws a stone vertically upwards. So velocity must decrease. Since it is vertically upwards, the velocity must decrease. This one shows an increase in velocity, so this is wrong. So B shows a decrease in velocity because the graph tends to the x-axis. D also shows a decrease in velocity because the graph tends to the x-axis. But then, because the stone eventually hits the stone first goes up and then it comes back. So there must be change in direction. It hits the sea. It goes up, then it comes to hit the sea. So there must be change in direction. So D is wrong because D is showing the same direction. The velocity is on the same side. So D is wrong, even though it is showing a decrease in gradient, which would show terminal velocity. There is no change in direction according to D, yet there must be a change in direction since it goes vertically upwards and it eventually hits the sea. So the answer is going to be B because the velocity decreases to 0 from one direction and then it increases but the acceleration, the gradient is decreasing, so acceleration is decreasing. Acceleration is tending to 0, it is decreasing to 0 at this point here, which means the velocity is increasing, but it is reaching a point where it becomes constant. So it eventually hits the sea, but with a constant velocity since there is air resistance acting. So the answer is going to be B. Velocities on both sides, meaning there is a change in direction, and the gradient is decreasing, meaning that the acceleration is decreasing. So the answer is B. The skaters of masses 80 kilograms and 40 kilograms move directly towards each other and collide. Before collision, the heavier skater is moving to the right with a speed of 22 meters per second, and the lighter skater is moving to the left with a speed of 1 meter per second. After the collision, the heavier skater moves to the right. The heavier skater continues to the right with a speed of 8 meters per second. What is the relative speed of separation of the two skaters? Relative speed of separation. Okay. Let's begin by conservation of momentum to find the speed of the second skater after the collision, because they have not told us that the collision is elastic. So by conservation of momentum, total momentum before collision, I will set to the right positive, to the left negative. So for the heavier skater, it will be 80 times 2. Because the lighter skater is moving towards the left, so this will be minus. The mass is 40 times the speed is 1. Total momentum before collision should be equal to total momentum after collision. I'm just saying momentum is mass times velocity. So for after collision, the heavier skater continues to the right. So his mass is 80 times his speed, which is 0.8. Then we don't know where the other one moves, so let's just say plus. Total momentum of the lighter skater will be 40 times his velocity. Let's call it V. So let's first press the calculator and find V. So we have 80 times 2 minus 40. Then we subtract minus, I'm taking 80 times 0.8 on the other side, 56. Then I divide this by 40. So this is giving me V as 1.4, and it is positive, so it is to the right. So V is equal to 1.4 meters per second. Because it's a positive, it is to the right, because I consider the velocity is to the right positive. Okay, having got that, then we can find relative speed of separation. So relative speed of separation is going to be 0.8 is to the right, 1.4 is to the right, so I'll just say 1.4 minus 0.8, and I think this is 0.6 meters per second. So the answer is going to be A. The answer is A. The velocity time graph for an object of mass 2.5 kilograms is shown. What is the resultant force acting on the object? Of course, this graph is going to help us to find the acceleration, because acceleration is the gradient of a velocity time graph. So the acceleration is going to be, I'm finding the gradient, so that is 12 minus, I think this is 3 approximately. So minus 3 divided by 15. I think that is 9 divided by 15, which is, I think, 0.6. 9 divided by 15, 0.6. So the acceleration is 0.6 meters per second squared. So the resultant force is mass times acceleration, which is the mass is 2.5 times the acceleration, which is 0.6. So I'll just multiply this by 2.5, and this gives me 1.5 newtons. So the answer is going to be C. Which statement follows directly from Newton's first law? Directly from Newton's first law. Remember, from Newton's first law, when there is no resultant force acting on the body at rest will remain in its rest position, and the body moving will continue moving with uniform velocity in a straight line. So let's check A. A body remains at constant velocity unless acted upon by the resultant force. I think that is very true. A satellite in circular motion about the Earth has constant velocity. The velocity keeps changing because it changes direction. A water drop leaving a spinning umbrella travels at constant velocity, not at all, because the umbrella was spinning, it changes direction. The force acting on an object is equal to its momentum. No, force is the rate of change of momentum. So the answer is A. A resultant force causes an object to accelerate. what is equal to the resultant force? So we know that the resultant force is equal to the rate of change of momentum. So change in momentum per unit time, which is c. A skydiver falls from an aircraft that is moving horizontally. The vertical component of velocity of the skydiver is v. The vertical component of the acceleration of the skydiver is a, which row describes v and a during the first few seconds after the skydiver leaves the aircraft. So first of all, it is moving horizontally. Falls from the aircraft that is, sorry, it falls from an aircraft that is moving horizontally. Okay, so he himself may not be moving horizontally, he's falling downwards. The component of the velocity of the skydiver is v, vertical is v, and the vertical component of the acceleration of the skydiver is a. So assuming there is air resistance, of course the speed will increase, and that means acceleration is going to decrease as air resistance increases. As air resistance increases. Reason as air is because the speed increases, the air resistance also increases. As the air resistance increases, the acceleration decreases. So the acceleration must be decreasing. So it can't be constant. We eliminate A and C. Because the air resistance increases with the speed, it means the acceleration decreases. Because remember, if a person is falling, the weight is constant and the air resistance is in the opposite direction, the resultant force F is equal to the weight minus the force due to air resistance. As the air resistance increases, the difference becomes smaller, the resultant force becomes smaller. Remember, resultant force is mass times acceleration. If the resultant becomes small, it means the acceleration also becomes smaller. So the acceleration decreases. Then how about the velocity component? Of course, the velocity component increases until it reaches a constant value. So v, the vertical component of the velocity increases until it reaches a certain value, because they're saying which row describes v and a during the first few seconds. So v increases, but of course later on it will become constant. So the answer is going to be D. V increases in the first few seconds, but we know later on when the acceleration becomes zero, v would remain constant. So the answer is D. The ball is thrown vertically upwards from the ground and reaches a maximum height of 12.7 meters before falling back to the ground. So it goes upwards before falling back to the ground. Air resistance is negligible, that means the equations of motion can apply. What is the total time for which the ball is in the air? Total time in the air. Okay. So since air resistance is negligible, then equations of motion can apply, and I will basically use S equals to UT plus a half AT squared. So S equals to UT plus a half AT squared. So a ball is thrown vertically upwards from ground level and reaches a height of 12.7 meters before falling back to the ground level. Okay. So since I don't know the initial velocity and I don't know the time, so I have two unknowns here. I will not use that equation. Let me use I am going to consider the ball falling from the maximum height, from here, from the highest point. So remember, it momentarily stops before it returns. So it means if it is falling downwards, its initial velocity is going to be zero. Okay. So I'm considering it falling, where u is equal to 0, falling backwards. So I'm only finding the time from the top to the bottom when it is falling. So if I multiply that time by 2, I'll find total time when it is in air. So S, it is going to be falling a distance of 12.7 meters downwards. So I'll say 12.7 meters equal to initial velocity is 0 when it is falling, a half. Acceleration is 9.81, then times t squared. So let's find t. So I'll just say 12.7, multiply this by 2, divide by 9.81, and I find the square root of the answer. So that is 1.609. So 1.609 seconds. That is the time to fall from the top to the bottom. But since air resistance is negligible, the time to reach the maximum height is the same as the time to reach downward. So the total time is going to be twice t. So I'll multiply that by 2. And this is giving me 3.22 seconds. So the answer is going to be B. A snooker ball has a mass of 200 grams. It hits the cushion of a snooker table and rebounds along its original path. The ball arrives at the cushion with a speed of 14.0 meters per second and then leaves it with a speed of 7 meters per second. The ball and the cushion are in contact for a time of 0.6 seconds. What is the average force exerted on the ball by the cushion? Okay. They're in contact for a time of 0.6 seconds. So what is the average force exerted on the ball by the cushion? So we know that force is equal to the rate of change of momentum. F is the rate of change of momentum. So the change in momentum is mass times V minus U divided by T. So this is the mass is 0.2 kilograms to change to kilograms. V, because the ball rebounds, one velocity is going to be negative. So if I subtract, we have positive. So we have 14 minus negative 7. Because it rebounds, one velocity is negative since it is in the opposite direction. So the one with which it rebounds is going to be negative. Then divide this by time, which is 0.6. So pressing the calculator, I have 14 plus 7, that is 21. 21 times 0.2 divided by 0.6. So that is 7. So my answer here is 7 newtons. So the answer is D. A tennis ball tennis ball is released from rest at time t equals to 0 and falls through air for a long time. Which graph of its displacement against time t best represents the motion of the ball? Okay, it is falling through air. That means air resistance is not negligible. So it must reach terminal velocity. It must reach terminal velocity. So remember, if it is a displacement time graph, to show terminal velocity, the gradient will be tending to a straight line. So it falls through air. So this one is showing that the displacement is constant for some time. So here it means the velocity first decreases, then becomes constant. Because here the gradient first decreases, then it becomes constant. Yet the velocity must first increase because it is falling due to there's an acceleration. So the velocity must first increase before it becomes constant. B is also showing that the velocity decreases, then becomes 0. Why? The gradient decreases to 0, so the velocity is decreasing and it becomes 0. When the line is becoming horizontal, the gradient is 0. Remember, the gradient is the velocity. Then C shows that the velocity just increases up to infinity. So here velocity increases to infinity. That's what C shows, because the gradient is increasing to infinity. So it means the answer is going to be D, because the velocity first increases. You see the curve is going upwards, then it becomes a straight line. Velocity first increases, then it becomes constant, because the gradient first increases, then it becomes a straight line where the gradient becomes constant. So the answer is D. So terminal velocity is reached. The velocity first increases until it becomes constant. Lastly, in this video, the space probe Rosetta was designed to investigate a comet. The probe consisted of an orbiter and a lander. The orbiter had a mass of 170 kilograms and the lander had a mass of 100 kilograms. When the two parts separated, the lander was pushed towards the surface of the comet so that its change in velocity towards the comet was 3 meters per second. Assume that the orbiter and the lander were an isolated system. The orbiter moved away from the comet during the separation. What was the change in the speed of the orbiter? Okay, we are going to simply conserve momentum. We are going to use conservation of momentum. What is the total momentum before? The total momentum before was the mass is 270 in total. That is 100 plus 170 times 0, because it was initial at rest. Then after this, the lander moves downwards, and then of course the other one moves in the opposite direction. So for the orbiter, it will be its momentum. I'm using momentum mass times velocity. So for the lander, its momentum is going to be 170 times its speed v. And for the orbiter, it is moving in the opposite direction, so I'll say minus. Its mass is 100 times its speed, which is 3. So let's first find v. So it means 170 times v is equal to 300, which makes v to be 300 divided by 170. That is 1.76 or 1.8. So this is 1.8 meters per second. So the question is, what was the change in the speed of the orbiter? Remember, of course, it was initially at rest. It was initially at rest, so its initial velocity was 0. Now its velocity is 1.8, so the change is automatically 1.8. Okay, so let this be the end of part 2. See you in part 3. Bye bye.